So what do I mean? This theorem is very important because it characterizes injectivity of a linear transformation. I think it also applies to any other map. Yeah, that for one to conclude that a map is injective. Why am I saying that it is a strong condition that characterizes injectivity? Instead of checking for the other first condition, the other definition which I defined, that a map is injective, as in if two objects are equal, then we say that if a map is injective, if two objects are equal, then the images should also be equal. Then if the images are different, then the objects should also be different. Now, this is a strong condition which characterizes the injectivity of a map. Instead of checking for equality of images and the equalities of objects, one can easily determine the kernel. Yesterday we looked at how to determine the kernel of a linear transformation. So if the kernel is 0, then one concludes that the map is 1-to-1. So that's why I'm calling this strong condition, which should characterize injectivity of a particular map. So let us prove it. Now this is an if and only if statement. I don't know. I think in the year, I don't know which year you are in, but before this module is taught, there are those modules where you are taught. There's a certain module where you are taught how to prove things. So if we have an if and only if statement, we have two sides to prove. There are two sides which we are supposed to prove. What are those sides? You see, the theorem says that T is 1-to-1 if and only if kernel of T is 0. So you suppose that T is 1-to-1. So for the forward direction, suppose T is 1-to-1. Suppose T is 1-to-1, then we show that the kernel of T is 0. So you first assume that one side is true. There are two sides. What are those two sides? T is 1-to-1, then the other side, kernel of T is 0. The first side is T is 1-to-1, the other side is kernel of T is 0. So suppose that one side is true. Suppose T is 1-to-1, then show that kernel of T is 0. Then we shall also look at the other side. So if you want to show that the kernel of T is 0, if you want to show that a set is 0, you pick. Okay, a set you want to show that a set contains a 0 element, something of that sort. You pick an arbitrary element. You pick a certain element from that set, then you show that it is 0. So if we pick an element from the kernel, and we show that that element is a 0, then we shall conclude that the kernel is 0. Yeah. So to prove that, what have I said? To prove that the kernel is 0, pick an element, an arbitrary element, which you don't know, whether it is a 0 or not. Pick an arbitrary element. If you show that that element is a 0, then we conclude that indeed the kernel is 0. So that's what we are going to do. So we let W, maybe I use V. Let V 1, let V be an arbitrary element, the kernel. Let V be an arbitrary element in the kernel. Then by definition of the kernel, yesterday we defined what the kernel of the transformation is. If V is in the kernel, then from the definition of the kernel, from the definition of the kernel, if I say that V is in the kernel, we have that PV is 0. TV is 0, but T is 1-to-1. But T is 1-to-1. T is 1-to-1. But T is 1-to-1. Therefore, TV equals 0 should be the same as the T of 0. Like that. So I have TV equals T of 0. And the map is 1-to-1. And the map is 1-to-1. Therefore, this implies that V is equal to 0. So I picked my V from the kernel and I've been able to prove that it is a 0. Hence, the kernel of T is 0. So that is the first side. Then for the other side, that is the forward direction. For the other side, there are two sides here which we are supposed to deal with because of that if and only if statement. So for the backward direction, that's what I mean. We suppose that kernel of P is a 0 set. Then we show that suppose kernel of T is a 0 set, then we show that T is 1-to-1. So what do we, first of all, you have to first understand where you are going. What do we need to show? We need to show that T is 1-to-1. That's what we want to show. So what does it mean by saying that T is 1-to-1? Or what are we supposed to show? From the definition, we are supposed to show that if T V1 is equal to T V2, then V1 should be the same as V2. That's what we are supposed to show. So meaning that I'm going to start by assuming that TV1 is equal to TV2. So to do that, we let V1 and V2 be in V, be vectors in V such that T V1 is equal to T V2, like that. Then if those two are equal, that is the same thing as saying T V1 minus T V1 minus T V2 is equal to 0. It's the same thing as saying that. Then this is the same thing still as saying, because T is a linear transformation, T V1 minus V2 is equal to 0. So the difference V1 and V2, I'm claiming that it is taken to 0. So T V1 and V2 is taken to 0. And anything which is taken to 0, it is in the kernel. So this implies that V1 minus V2 is in the kernel of T. But kernel of T is the 0 set. Kernel of T is the 0 set, therefore if V1 minus V2 are in the kernel of T, therefore V1 minus V2 should be a 0. Should be a 0, so that V1 is equal to V2. That V1 is equal to 2. Hence, the map is 1 to 1. Hence, T is 1 1. There is another theorem here which I'm going to state, but I'm not going to prove it. Then I will later on work out an example. So we have the following theorem. It states that let T taking V to V, that T be a linear operator. To be a linear operator. Yesterday we defined what a linear operator is. Linear operator takes the same thing to the same thing. Yeah, it is still a linear transformation, but a linear transformation which maps the same thing to the same thing. In particular, it is called a linear operator. So let V be a linear operator. Linear operator on a finite dimensional, finite dimensional vector space, finite dimensional vector space V, then the following